In this video, we will see some sensible intuitions and expressions for enthalpy. This is how we started when we derived enthalpy from Legendre transformation. Now from this step onwards, let's go in a slightly different way. For this du, let's substitute the expression from the first law. Now dH is equal to del Q minus del W plus PdV plus VdP. Substitute PdV in place of del W, the work term. Collecting the terms, dH becomes equal to del Q plus VdP. Now in numerous practical processes, the pressure is not varied, especially in many reactions and phase transformations in materials. Now what happens to this equation when the pressure is considered to be a constant? It is also called as isobaric condition. The VdP term disappears and dH becomes equal to del Q. This gives a very intuitive meaning to what is enthalpy change. It is the amount of heat exchanged in a process when the pressure is not disturbed. That is one of the important meanings of enthalpy. Now let's see another meaning from a slightly different derivation. Here we start from the same step, dH is equal to du plus PdV plus VdP. Again, when pressure is constant, VdP term disappears. dH is equal to du plus PdV. In integral form, we can get a finite change. The capital delta H is equal to delta U plus P delta V. This is the change in enthalpy between two states. Now imagine we have a space with some constant atmospheric pressure P and consider the system to be under this pressure. Let's say a solid with volume V. Let's say this is the final state and imagine the initial state is zero volume of the system, meaning it does not even exist. If that is the initial state, then the enthalpy and internal energy are also zero. Now we can write this equation. Delta H is H minus 0, where H is the final enthalpy. Similarly, delta U is U minus 0 and P delta V is P multiplied by V minus 0. The final enthalpy then is equal to U plus PV. Now look at the last term. It is actually P delta V, which is the work term. What is this work? It is the work done by the system against the external pressure P in order to exist. In order to appear with a certain volume V, it has to do some work against the pressure. Now this is an interesting meaning for enthalpy. It is the addition of this work to the internal energy. Now consider the process like mixing of components in solutions, compound formation and phase transformations in materials. We can think about enthalpy change in these cases. H is equal to U plus PV. We have already seen what is internal energy. U is the summation of all the potential energy, which is the bond energy, and the kinetic energy, which is the energy of vibration, translation and rotation of atoms and molecules. When we say enthalpy change, it would be change in these quantities plus a work term. Remember, enthalpy change is also the heat exchange at constant pressure. Therefore, you can imagine that these changes manifest as heat exchange. That is an interesting meaning for enthalpy change. Alright. There is an approach called quasi-chemical approach, which treats enthalpy change to be equal to only the bond energy change, since it is often much more dominating than the other terms. Of course, this approach is not accurate, but it is quite useful. We have seen about the bond energy or the potential energy between atoms in the video on internal energy. When the atoms are infinitely far away, the potential energy between them is zero. It gradually decreases when the interatomic distance decreases and reaches the minimum at what is called the equilibrium interatomic distance. It can only increase with further reduction in distance. Therefore, the potential energy curve looks like this. The bond energy is this energy. Note that This value is negative since it is below 0, and you can sense that stronger the bond, more negative will be the bond energy value. Let's say the bond energy among A atoms, the AA bond energy is this. It is denoted as epsilon AA. Similarly, for some other element B, the BB bond energy is this, denoted as epsilon BB. When AB atoms are reacting or mixing, AB bonds are possible. The bond energy is denoted as epsilon AB. Now, according to quasi-chemical approach, the enthalpy change is the change in the bond energy alone. Epsilon AA and BB may be quite different. The epsilon AB may be higher or lower than the average AA or BB bonds. It depends on the type of the component, the specific A and B. For example, the bond energy of copper and nickel will be different from that of copper and iron. Therefore, the change in bond energy during mixing is epsilon AB minus the average of epsilon AA and BB. This will be the enthalpy change per AB bond formation. If this value is positive, it means that AB bond energy is higher than the average bond energy of AA and BB. Then the curve is going to shift upwards. It also means that the bond between AB is weaker than AA or BB. Remember, the more negative the bond energy, the stronger the bond. Here it is going up, so it is weaker. When enthalpy change is negative, it means AB bond is stronger and the curve is going to shift like this. Till now we are talking about the shifting of this curve up and down. In fact, even equilibrium interatomic distance changes depending on the component temperature and composition. Alright, when delta H is positive, it means there is a repulsion between the AB atoms. It means when the bond forms, the potential energy goes up and heat goes into the process. The process takes some amount of heat from outside. When delta H is negative, it means there is an attraction between AB atoms. It means when the bond forms, potential energy goes down and heat comes out of the process. These are called the endothermic and exothermic processes. Heat going in and coming out respectively. With this understanding and enthalpy, let us go for understanding the Gibbs energy in the next video. See you.